Ok. Buenos días a todos. Esto es la red LAFMAT, Red Latinoamericana de Física Material Condensada y Ciencias Materiales. La red LAFMAT es una red conformada por profesores de distintas universidades en Latinoamérica. De Perú, la Universidad Nacional Mayor de San Marcos. De Brasil, la Universidad Federal de Pernambuco, en Recife y en Caruaru, ahora. Y la Universidad Federal Rural de Río de Janeiro. En Chile, Universidad de San Sebastián, en Puerto Montt, Universidad Católica del Norte, en Antofagasta, en Colombia, Universidad Nacional de Colombia, sede en Bogotá, y también Ximena Velázquez. En México, el Cinvestav de México y, y también el Centro de Estudios Avanzados de México. En Venezuela, Universidad de Zulia. El día de hoy tenemos un invitado especial, que es el doctor Rodrigo Arouca de Albuquerque. Él es un postdoc de la Quantum Matter Theory, del grupo de Quantum Matter Theory de la Universidad de Uppsala. Hizo su doctorado en la Universidad Federal de Río de Janeiro eh, y también ha tenido visitas en el Institute for Theoretical Physics de la University of Utrecht. Ha trabajado en física y materia condensada con sistemas fuertemente correlacionados y materiales topológicos. Él es especialista en mecánica cuántica con campos y métodos numéricos. Entonces, es un buen amigo también. Eh, Quiero mencionar que el día de hoy también tenemos como panelistas al buen amigo Alexander Hernández de la del Centro Atómico de Bariloche en Argentina, que va a dar su palestra la próxima semana también. Tenemos Cambridge. También está el amigo Augusto Moreira de la Universidad Federal de Pernambuco y de sede en Caruaru. El profesor Augusto Moreira es es a big professor, es un profesor muy importante en el nordestino y muy poderoso. Tiene mucho financiamiento, ¿no? También. Por eso estoy ahora estoy en Caruaru visitándolo. Profesor Mauro Doria, del eh, Universidad, vos se conoce también, Rodrigo, del Universidad Federal de Río de Janeiro. Perfecto. Y también se van a ir incorporando más profesores en el transcurso de la palestra de Rodrigo. Perfecto. También está el profesor Sergio Conejeros de la Universidad Católica del Norte en Antofagasta, en Chile. Está también el profesor Arturo Martínez, que se acaba de conectar del Cinvestav de México. Bien, se van a ir conectando más profesores. La palestra va a ser en inglés, en English, y você puede presentar agora sus diapositivas y empezar su palestra. Obrigado.
Okay, so I just need a minute here to share my screen. So, can you see now my presentation in Zoom?
Yeah, we can see now. You can start.
Okay, nice, great. So, yeah, so good morning for everyone. Also, good afternoon for people that in Europe. So it's a great pleasure to be here. I really appreciate the invitation, and I think also it is a great initiative. So also I'd like to thank you both for the invitation, especially Isaias, that unfortunately is sick, so he cannot be present, but I really appreciate. And also for organizing this amazing initiative. So unfortunately, I was not able to attend the previous meetings, but for sure will be in the next ones. So today, I would like to talk to you about this work that we did. So let me try now to change here for a laser pointer. Yeah, I hope that you can see now. So this work started when I was doing my big exchange that I did in the Netherlands in the group of Professor Cristiane de Moraes Smith during my PhD. And it's as you can see here, it's there's a lot of people in the paper. Is an experimental and theoretical collaboration. And basically, what we did in this work is that we the group of Professor Jinfeng Jia from Shanghai had some bismuth samples on top of indium antimonite, and they showed that this structure forms some self-assembled the bismuth flakes on the structure. They form some self-assembled fractal structures. So they had a previous paper where they showed this, but something that they do not publish were some measurements that they did for the electronic density in the systems. And they saw actually that you have some features there that I will try to convince you that actually are signatures of topological phase in these materials. So this was something that started, as I mentioned in my PhD. And then we tried to do this, the modeling of these materials. Then this was finished when Robert Canielas joined the effort. So he was a master student, the co-supervisor, Professor Cristiane. And also Lumen, that's a PhD student in her group, joined and did the theoretical analysis of these materials. And then we were able to finish this project and argue that these are topological states. So this work was finished last year. It's available on arXiv, and actually is in press in Nature Physics, and we expect to be present to appear next week. So for this presentation, I will just start explaining what a topological state is. Then I was explaining why bismuth actually is. I was talking a bit with Professor Schultz in the beginning on how bismuth is a wonderful material. And here, I'll show also that's a wonderful material for topology. Especially, and then I'll show why we expect this why we expect that these flakes that they measure there should be topological. And then I'll discuss a bit what fractals are and why it's interesting to find these topological states in fractals. And then I'll turn to our work and try to explain exactly what the methodology was to try to model these materials and what we found and what needs to be done. So this presentation, I'll cover many things in the presentation. So feel free also to interrupt me at any time and ask questions if something is not clear. But also, of course, in the end, I'll be happy to discuss with you if you like to explain, so you understand something better on the presentation. So just starting now. Before starting with the scientific part, I'd like to say that I'm a postdoc in Uppsala University, in the group of Professor Annika Blackschaffer. So for those that never heard of Uppsala, is a city in Sweden, and it's actually quite close to the airport. The airport actually is closer to Uppsala than from Stockholm. And Uppsala University actually is a quite big university. Now I'm in my office here. It has a huge physical department and also physics department, sorry, and also material science here in general is quite big. So the division that I am part of is the material theory division. Mostly is made of people that work with ab initio methods for magnetism, ultrafast magnetization, spintronics, and biomaterials. So it's quite strong, I think, in these areas. But Professor Annika Blackschaffer and also Jorge Caio, that actually is Peruvian. So he's also, I think, a nice person to be present in these meetings and also give talks. They work more with these topics of quantum area theory. That's closer to my is actually what I do instead of these topics more for ab initio calculations. And basically, the topics that they work on and also I work on are mainly with superconductivity. Is my formation actually in Brazil was working in superconductivity, but also looking at non-crystalline systems like fractals that I'm going to talk about. And lately, we have been working a lot with no-emission in open systems. So it's an area that we have been working quite a bit. So it's also like I'm also taking the opportunity here to explain a bit what people do and also to show a bit to Shuppi, especially a guy that's also from Latin America. So I would like now to start the scientific part and say that explain a bit why it's interesting to look at topology at all. And the way that I like to understand this is actually going back a bit to our basic course on condensed matter and think on how to understand the properties of a solid, right? So in our course on condensed matter, usually you think that, okay, a solid is just is an arrangement of atoms in a crystal. And then when you arrange these atoms in a crystal, you form bands. And just knowing the number of electrons basic of the bands, you know if the material is a metal, is an insulator, a semiconductor. And there you know the properties that it has. You know if it's conducting or not, you know if it is, I mean, electrical or thermal conductor. You also know some properties it should have, it shines or it's not. But this is something that helped a lot us to understand the view of these materials. But of course, you have more interesting phenomena that also appears. For instance, you have this spontaneous symmetry breaking. That's something that if you have correlations are quite important. And then it explains a lot of things that are interesting that appears in material, right? If you think about magnetism, superconductivity. So it's something that, I mean, for sure people here in the audience are quite familiar with. So it changed a bit our understanding of the materials. This was something from from last century, right? That you have this London theory of phases and phase transitions. And a new addition for this understanding actually are topological materials they're interesting because they are neither described by this understanding of spontaneous symmetry breaking, that you have all the parameter and spontaneous symmetry breaking, but also, and although you can use band theory to understand some properties of them, they are kind of in between metal and insulators. So, for instance, here this is a cartoon showing more or less how we can think about topological insulator, for instance, that you have a material that in the bulk is an insulator. But in the edges, you need to have some states that actually are conducting. So actually, the edges of the system behaves more like a metal. So it's quite interesting. It's something that's very fundamental because related to some quantization of some properties in this material, as I will explain a bit. And is a kind of new way to think about how can understand properties of a solid that's not on this sheet. So to explain a bit, I mean, this is a talk, and then I need to explain other things, also my work. So I'll not be able to, of course, give a lecture on it. But I want to at least give you a bit of a flavor why it's, I mean, how it appears and why it's important. So to do that, I'll start with I think the first example of a topological phase of matter. That's a quantum Hall effect, and the idea here is really is something close to the traditional Hall effect that we see just in our basic course in electromagnetism, that you have a material, you apply some magnetic field on it, and then you measure the transverse conductance that you have here. So you measure if you have some voltage associated, transverse voltage associated with a current that you pass through it. So what von Klitzing and others showed is actually if you have a semiconductor that's very clean and you go to very low temperatures with a very high magnetic field, if you measure this transverse resistivity of these materials, instead of being something that just linear or quadratic with the magnetic field, actually you see something that you have this kind of steps here. And these steps are very precise. They are so precise actually that nowadays you can actually use them for standards. So for instance, the definition of kilogram actually is using this kind of effect. It's called the quantum Hall effect. So if you want to understand how this occurs and also why it's so interesting, it's nice to just think about how you think about basically the modeling of this material here. So because of time, I'll not be able to go into detail. But I think a modern way to interpret this, so I mean, I'm showing here some experiments from the 80s, and this paper here is a paper from the 2011. So of course, I mean, you had other ways to understand this before. But a way that I like to talk about this is actually thinking that since you're applying a magnetic field in the system, you know that you have some kind of, you create some currents there. And also you change a bit what is the canonical momentum of your electrons. So in some sense, if you think about the position of these electrons and you project this in the bands that are occupied, you see that you don't have commutation between X and Y. What's kind of interesting, right? Because if you think about quantum mechanics, is one of the first things that you learn, right? I mean, momentum and position don't commute, but the different positions should commute, right? So actually, this is showing us something quite interesting, that actually, if you look at the bulk of this material, it's not something that is close to atomic insulator. So a lot of atoms, a lot of atoms that are just displaced, but actually is a quantity that fundamentally differs from that. And this difference is quantified, sorry, by an integer called the chair number. And what's interesting is that if you look at the figure that I showed before, that is showing the quantization of resistance of these atoms, sorry, of the quantization of resistance of the transverse resistivity in these materials, you actually have the quantity that appears there multiplying these plateaus is a quantity called chair number. That's precisely this one. So this actually was the understanding that people had in the 80s of this quantum Hall effect. Here, for instance, I'm showing a way to think about this, and it's based on some lecture notes that we have. That basically it's understandable that understood that you have this, because basically when you apply this magnetic field, create some London levels in this material, and these London levels in the surface of these materials will create some kind of special states that transmit this quantum conductance. So these states they appear in numbers that are determined by the chair number. So then you understand why it's quantized the conductance that you have from them. So this is related a bit to the thing that I showed in the beginning, that if you have this kind of special state, in the surface of them you have these protected edge states. So this is I mean, the way to understand this in this case of the quantum Hall effect, when you think about some orbits that the electrons make in the material when you apply magnetic fields, and the skipping orbits that you actually cannot close the orbits on it in the surface. So this, what's interesting here is that if you now if you just think about conductance as you usually think, and you just compute electrical you apply electric field there, you see the response, and then relate this to the conductance. This was what done by Towles, Komoto, Nightingale, and the nines. You see that actually that here you're going to have some quantity that's precisely the chair number, and this quantity actually depends on the band structure of the material. So this is basically the momentum space representation of what I showed before in Lewis space. And what's interesting here is that actually this quantity here is very robust, does not depend on the details of the band structure that you have. And it's something that is related to something called topology. That's a field of math that actually studies surface. I mean, not on surface, it studies actually the formation of some property or some quantities, but you actually can relate to study of surfaces. So, for instance, you can actually think that a property that a surface has that actually you cannot change by continuous transformation, looking at the number of holes that it has. So in this sense, if you have if you can stretch the surface and not change the number of holes on it, it will be a topological equivalential difference. So what's interesting here is that, I mean, you can see that the materials, you can have some property that in this case is called the chair number that's related to non-commutation of X and Y. And basically you can have different phases related to different integers of that. That's also related to the number of edge states that you have. So basically this is a property that's very robust, will not change if you still have an insulator. So you need to have a gap closing to change this number. So it's a very robust quantity and explains why you have a very robust response when you look at this quantum Hall state. So this is a very quick explanation about how you get this Hall conductance, why it's important. And what's actually interesting on that is that this is not applied just for the example that you have a system in a magnetic field. And also, sorry, this is also related, I should have mentioned this before, that is what's called bulk band correspondence, that you have this response in the bulk related to some response in the edge. So it's not something that is applicable only for this example that you have to the system magnetic field, but actually applies for a lot of different cases. So you have actually like a classification called Lenzing-Bach classification that gives you some symmetries in the dimension of the system. Basically tells you if you can have topological phase and which kind of topological phase you have. So I'll not have time to go to the details here, but I'll be happy to answer a question about this if someone has, but perhaps in the end of the presentation. But so here, the important point is that you have gap bulk with conducting surface. So this idea of having this topological insulator. For different symmetries, you have different kinds of edges or invariants. and that the phases are robust and not related to symmetry breaking. And also it is not exactly what was the subject of the Nobel Prize in 2016, but related to that. And I really recommend you to see the announcement if you have not seen, because it's quite nice and I think explains in a very pedagogical way these topological phases. So we saw a bit this emergence of this quantum Hall effect, how it's related to quantized conductance, and it's also these edge states. But as I mentioned in the beginning, you need to have a very high magnetic field and very low temperature to observe that. So if you have this kind of quantized conductance, is actually, I mean, you can use it to redefine units, but also in principle can be used, for instance, if you want to transport electrons, right? You're transporting electrons without dissipation. So it can be something quite nice. So is it possible to obtain them without having magnetic field or very low temperatures? So this is a question in the field for a long time. So there has been a lot of interesting advances on that. And actually, so there are some papers from 2007 where actually were able to observe this quantum Hall effect at finite temperature. But still, but the price that you pay is that you need to have an extremely strong magnetic field to see it. So here you see a magnetic field of 29 Tesla. But actually, this question of obtaining, so if you want to obtain the quantum Hall effect without the magnetic field, is a question in the field for a long time. And I think it's from the rest of my knowledge, the first one to think about this actually was Haldane to propose a way to do it. And basically, they propose that you should have a very complicated structure in material that actually is very special, is very difficult to find. But later, people realized that actually a way to do that was to play with something with spin-off coupling. Basically here, what you do is that you have some kind of structure in the material that you basically spin-off couple, you can think that you have a kind of effective magnetic field, but that you see different from spin up and down. So doing this kind of reasoning, Ken and Melee were able to do a model where they see this kind of effect. In principle, they predict this should appear in graphene. But actually, spin-off coupling of graphene is quite low, so they could not see it. But in principle, if one could do this model that they propose, it would be quite interesting because basically what happens is that you have this kind of same technology of the quantum Hall effect, that you have some current circulating in the edges of your material. But now, as I mentioned, it's like each spin channel, you're going to see a different magnetic field. So spin up will actually circulate in one direction, while spin down will circulate in the opposite direction. And when you look at the conductance, actually, you don't have, if you sum both conductance, actually, it will give you zero. So you don't have the quantum Hall effect, but you actually have something called the quantum spin Hall effect, that you have a half quantization of this conductance for spin up and spin down. So they cancel if you sum both, but in principle, you're going to have different for spin up and down. So now it's nice because I actually know that there is some quantity here and spin-off coupling that we can use to have these topological phases even without having like very high magnetic fields. So in principle, you should look for materials that have very high spin-off coupling to try to obtain this kind of interesting phases. So a material that has it by itself is bismuth, because bismuth is a very heavy atom. So in principle, we expect to have a very high spin-off coupling. So there is this very interesting science paper from 2017, where they show that if you have just a layer of bismuth on top of silicon carbide, you form a honeycomb lattice here. And it is honeycomb lattice, you see that you have this quantum spin Hall effect. So the system actually is not really, when you look at the system here, it's a bit difficult to measure this effect. But you see here, I mean, this is a very nice paper I refer to read if you want to see the details. But basically, they show that you have this idea that you have a system that is an insulator in the bulk, and you have these metallic like edge states in the system here. So I'm not sure if they were able to measure the half conductance in this setup. I think they do not, but at least they show that this is something that you have the quantized states there that are protected and quite robust. And something that's actually interesting is that bismuth because of this very high spin-off coupling, does not show only this phase, but also there is other kind of topological phase that can appear when you add more ingredients to it. So one ingredient that you can add is crystalline symmetries. And then there was some work showing that if you add this crystalline symmetries, actually you can have states that are not only live in the surface of the material. I mean, not something like the edge, but actually you can have something that's called a high order topological insulator, that the states live in corners of the system here. So for instance, this is just a cartoon of how they look like. And actually, this was proposed in 2017. In 2018, there was already a realization that if you take just 3D bismuth, actually you have this high order phase rate. So here it is a cartoon of how the system should look like. You should have states that are not really surface states in 3D, but actually are hinge states. And they were able to measure it using these different platforms here. So they show that you have robust states that live in the edge of the system that present some quantized conductance. So bismuth, I mean, there's other different cases of bismuth that show that also have other interesting states. And the group of Professor Jingfeng Jia from Shanghai University was studying bismuth in 2019. And basically what they saw is that this was the measurements were done by Shen Liu. That at the time was a PhD student in his group. And basically what they show is that if you have just a layer of bismuth here on top of indium timonite, you actually forms by itself some fractal structures here. So you see here that actually it's not like you have a very big fractal. In a fractal here, I'm going to explain a bit with more detail what a fractal is, but you see that when you look at these flakes, it's not that you have like a triangular lattice or a honeycomb lattice, but actually something that's quite homogeneous here, and also have a lot of holes on this kind of structure. So this by itself is quite interesting. You see that you have some, I mean, it's a bit mesoscopic that you have many different areas. But something that's quite interesting is not in this by itself was a physical review lattice. But something that's quite interesting that's not in this paper is that actually when you look at a flake here, and this I will show in more details what I will explain more details what I'm showing in another slide. But if you just do some scanning tunneling macroscopy of the system here, looking at the density of states, you see that close to the Fermi level, actually you have some states that are localized both in the corners of the flake, but also in the edges of the system, both the outer edge and the inner edge of this kind of samples. So as I try to convince you that these topological states usually are related to the fact that you have this kind of state in the edge, the questions that they ask themselves and also ask us is whether these actually are signatures of a topological phase. So this is our interest in look at these materials, and I will explain to you how we model there and try to answer this question. But before doing that, I would like to explain what kind of structure they are seeing here and why it's interesting. So as I mentioned, this is something called a fractal. And I'll show you actually how we can build a fractal and what the properties it has. So imagine that you just start with a triangle, a boring triangle that, I mean, we also are very familiar with. And it has some area, A0, and some perimeter, P0. And now we can just play a game with it here and try to take the middle point in this side here, also in this edge and this edge, and then do some line on it and take this out of the triangle. So if you do it, we're gonna end with this figure here, and then we see that doing that, since we're taking part of it, we are taking the area that has is smaller than the original area, but doing that actually is creating more perimeter here, right? Because you have the outer perimeter of this triangle, but also you're creating some perimeter inside, so you're creating more edges for the system. And we can do it again. Now we take each of these small areas and we do more holes. So doing that, again, we're diminishing even more the area and increasing the perimeter. If we do it now an infinite number of times, we're going to see that actually we end up with some structure like this. And this structure is very special. It's called a fractal. And it's a structure actually, I mean, in this case, specific case, the way that we built, it's something that has zero area because you're taking out an infinite number of triangles. But the perimeter actually is divergent, right? Because then you're creating more and more surface, more and more inner area when you're doing that. And the thing that's interesting here is that if you now define the area of a system by how the volume, in this case, the area is to the system, changes as you change some dimension. Actually, you see that this system here actually is not two-dimensional, as I said, but actually something that has a dimension that's between 1 and 2, so it's 1.58. So this by itself is a quite interesting realization that, I mean, we're just playing games here, just doing holes in this material, or sorry, this lattice. But then we end up with something that has some dimension that's between 1 and 2, since, I mean, it's really something that's not only perimeter, but these areas go to 0, right? But what's interesting here, fortunately the video is not playing, but actually if you zoom in here in many generations of this triangle, actually what you see is that if you zoom in more and more and more, you're gonna see the same structure repeating itself. So this is a characteristic of fractals, actually is actually what's characterizing fractal, and something called self-similarity. So it means that you don't have a typical scale on it, but actually as you zoom in more and more into this material, in this mathematical structure, you're gonna see the same thing repeating itself. So of course, it's a mathematical abstraction because then you need to have something that you really don't have a typical scale, and we know in life things usually have length scales. But it's quite nice to understand a lot of properties, and it's something also quite beautiful. So actually, even if you never heard about fractals before, you've probably seen some of them. In fact, I mean, you see them in nature, as I'm going to show you, but also in art is very common. So for instance, here it is the ceiling of the La Sagrada Familia in Barcelona. And then here you can see that we have this kind of structure here that repeats itself and has this kind of notion of self-similarity, but of course in a finite sense. So it's something quite, I mean, aside from the fact that they are really interesting, the fact they have no interdimension, they have this property that's self-similarity, they are also quite beautiful to look at. So also I think is a reason, also another reason why they are so popular. If you think now about topology, there's another thing that's interesting because we are thinking about, maybe you can think, okay, I look at a lattice structure like this. So I have a material maybe that's made of something like this. I can think of the bismuth fractal I showed before. Is possible to have this thing that has topological states? I mean, how I look at this edge state, something like this, how I look at this quantized conductance. And what's nice is actually due to this self-similarity they should have, you don't have translation bias. You cannot have a lattice, right? It's repeating itself. So from a technical point of view, when you want to characterize the system is very challenging because you cannot have like a band description of them very easily. Also, since you're creating holes on it, you're creating more and more edge and corner states. So if you want to use these states for some technological application, you're actually creating more of them. And I'm going to show some examples and they sit at different energies, what also can be quite interesting. Also, there is a point that you don't have really integer, you have a non-interdimension of the system. So say this, in the limit that you really create a lot of holes and you have a true fractal, you actually sit in between these different dimensions. So is this something, how we should think about this? Is this something that we have two dimensions with a lot of holes, or really something that's is basically a typical one in the system? So I think by itself is an interesting question to think about topology in these states. So there have been a lot of studies of these fractals since they are so nice. There have been some papers since 2018, for instance, thinking about theory of them. And then I think since this kind of quantum Hall state was the first legislation, also is one easy way to get topology is just applying magnetic field into the system. People have thought about how to look at this state. So for instance, here, this is a bit technical. This is a turbine Hamiltonian, and you are applying basically a magnetic field in a lattice. So basically, you do this by something called pile substitution. The details are not important, but basically, but of course, I'll be happy to take questions on it if someone works on it and want to know more details. But the main point here is that you are creating this thing that you have to the material with a magnetic field, and then you see how it responds. So this is based on this work here by Michael Fremley, and showing what they obtained there. And basically what they did is that they took a square lattice, and then they were piecing a hole on it and tried to see whether you have the same phenomenology of the quantum Hall effect. So they did that both computing this quantity that I showed you before, the Chair number, But also they also did this experiment that you really have you have DDP, you induce a current, and you measure the transverse voltage that you have. So basically, looking at the Hall effect. So looking at the Hall conductance here, you have this is a bit of a technical point. I'll ask you to not focus on the colors here so much, but just understand there's a way to measure this Hall resistance that they have. And basically, these are the different plateaus that you saw in the first figure by Klitzen and others. And basically, the point that actually here you still have plateaus of the system. So here, for instance, if you not have a lot of holes, this is how it looks like. You have a different quantization of the chair number. Sorry, different quantization of the Hall resistance. But as you're making more and more holes on it, basically you are destroying this kind of topological phase. And the same thing occurs if you measure what's called the share number, so using this topological invariant in both of the system. So long story short, basically they show that you can have also this phase, but usually actually the fact that you're making this in fractal kind of destroys a bit the topology, although it changes its features qualitatively. But it was something interesting that they show that this can work. Also, if you look at this high-order topology that I show you for bismuth, it also occurs. Actually, there's a work from, there have been works from other people, but also this one was by a group in Brazil, from Lucas Lage and Professor André Latiger from the Federal University Fluminense in Rio, Niterói. And they show basically similar things, that you can have high-order topological phases, and the states. Something that's interesting here that they show that the states live in corners, both the outer inner corners and also inner and outer edges of the system, and they appear in different energies. But I'm not going too much into detail on that. So this is something that, in theory, actually there are some papers, theoretical papers that investigate the topology of the systems. And actually, if you look at nature, you see fractals everywhere. It's something very common because basically, as I mentioned to you, a characteristic of this fractal is that you have the self-singularity, right? And basically, you can relate this to optimizing ratio and perimeter area. So now I'm going to start talking something that's not really my field, so I'm not able to answer questions so much on the specific papers. But you can see that fractals are present, for instance, if you look at plants. So I think this Romanesco broccoli is the example of fractals usually people think of. Also, they are present in rivers. And even if you start to think a bit about things that are a bit more complex, and if you want to think about lattice structure, oh, sorry, there's some problem here on the animations. But also, if you look at molecules, you can make these fractals occur. And if you look at your brain, actually, you can see that you have, this is also some nice work by a group in the Federal University of Rio de Janeiro, looking at folding of neurons in brains of mammals, and they show actually that if you look at this folding, it's like folding of paper, and there's also obeyed this kind of this fractal. So they have like also non-integer dimension if you look at how they behave. And even like for us in physics, if you look at just a metal-insulator transition, you see this kind of things that have this self-similar behavior with a non-integer exponent that's basically related to a fractal. So this is a beautiful science paper from 2007 looking at metal-insulator transition, and this interpretation in terms of fractals was from 2016. So in some sense, when you have phase transitions, you have criticality, and criticality also you can associate with self-similarity. So you are hopeful then that, okay, I have all these very nice, fractals are very common nature. So if I go there and measure things, I'll be able to see fractals, right? But actually in materials is not so common. And this is because I think when you think about this formation of the lattices, usually you have forces that are more volumetric in origin that form this kind of lattices. So in most cases, you're not going to see these fractals, and also they're not a crystal, right? So you're not going to see them forming naturally. And this such the case, actually the group in Utrecht that was also, was led by Professor Cristiani and Professor Ingmar and the design was done by Sander and the experiments by Marlu, they were actually be able to actually build this fractal lattice and show actually that you can actually have a tight binding model in fractals. And I think this was such an achievement that was the cover of Nature Physics. So they're not really common in natural materials. It's not common to see lattice made of fractals. So it also shows how this result from the group of Professor Jinfeng Jia was a very nice achievement to see this kind of fractal flakes in materials, something very special. Using these metamaterials actually has been some work in topology. I'm not going into detail, but just to give credit for them. I mean, this in both photonics and also acoustics, people were able to show this quantum spin Hall state and also this high-order states. But for us, I think the thing that's interesting is really starting with this bismuth on indium timonide and understand if they are topological or not, because it will be interesting. That will be a first realization of this topological states in a fractal lattice in condensed matter. And for us, I think it will be nice because if we understand the states well, we can maybe enter a field and start to actually look at all the states, right? Because I mean, if you think about this history of topological state that I mentioned to you in the beginning, we have the quantum Hall state. From it, we went to the quantum spin Hall state, and then this opened the door actually to other realizations and to understanding of other ways to realize this state. So I think for us, it's quite exciting because it's a way to actually. We don't think it's something that settles like the field, but actually opens the field for new investigations. So to understand this, what we did, I mean, and this I will describe the theoretical part of the work. So we have basically this material that is flakes of bismuth. And as I mentioned to you, bismuth is a material with a very high spin-off coupling. So basically to describe the theory of the system, we're going to do two approaches. One of them is the muffin tin method that we're going to start with a free electron. And then we add some potentials that's going to confine the electrons to some region, and then we introduce this spin-off coupling. And the other way is to do this tight binding method. So now we're going to start with the muffin tin, and then we're going to go to the tight binding. The muffin tin was done by Robert Canellas, that was a student from Utrecht, and as I mentioned, was co-supervised by me and Professor Cristiani. And now he's a PhD student in Radboud University in Nijmegen, also in the Netherlands, in the group of Katz Nelson. So basically, what we did is that we start with we model Tepinski triangle as something a lattice like this, and basically we have these different regions here that we're showing as these purple dots, and we imagine that the electrons in our lattice will sit there. So basically, to do that, we try to think, okay, if I have atomic potential, I would like the electrons to sit there, so it's more or less in these regions. But actually can think of equivalent problem that just think that I can use a repulsive potential that said the electrons will not like to sit in these holes of the system. And basically this was how we modeled this, that basically we have these potentials here. We don't want the electrons to stay in these points. And we start with a lattice like this, and then we put this in a grid. So basically, we have this kind of very simple idealization of how these flakes are, and then we just have this kind of we have a very big grid like this. We discretize our space. We do finite methods to solve the Schrödinger equation. Here there is missing an H for some reason. Sorry for that. But basically, this is the Hamiltonian that we have. That's just a kinetic part. You have a spin-off coupling. Also, here is missing a Rashba spin-off coupling that is given by the substrate. But basically, here what we do is that we playing with this spin-off coupling, and also with a potential that we approximate by Gaussian. We try to see whether we can find the same state that they saw in the experiments. So the first thing is that actually we saw that if we just have a kinetic energy without the spin-off coupling, we don't have any state that sits in the edges. So when introducing the spin-off coupling, we see that in low energies below the Fermi level, the state is just bulk states. So then when we go to close to the Fermi level, we see that we have states that sit in the corner, but not in the bulk. So it's the bulk of the system is insulated. And then as we increase a bit more the energy, we actually start to see states that sit in the edge. So I'm going to show you in a few slides that is actually quite close to what they see experimentally. So it's nice because at least in terms of the understanding of the state that they saw, we can kind of see then in the evolution of this method here, just by introducing spin-off coupling in the system. And this, sorry, I forgot to mention, this what I'm showing is just the density of states of the system. So bright colors are high density of states and dark colors are low density of states. So this is the reason why I'm saying here this is a bulk state, because it has occupation in the bulk, and while this one here is a corner state. To understand this also, to use a bit more of the parameters of the material, actually we also use a tight binding model. This was done by Lumen. That's what is a PhD student from Christian's group. And then what he did is that he used a tight binding model, adding X, PX, and PY orbitals that are relevant for bismuth. At least we use something close to bismuth close to the Fermi level. And here in the tight binding model, basically we assume that you have electrons that are really sitting on lattice. And then we did this modeling here of the fractal lattice of the flakes that they saw. And we imagine that now these electrons can either hop between different sites, or also they have some on-site energy that is shown here. So doing the side binding, actually you see again that, I don't know if it's visible here, but this is far below the Fermi level. We see that we have bulk states that have different symmetry, but they are bulk states. At the Fermi level, we have the corner states. And then we have edge states here that can be either in all edges or also just in the inner edge. So you notice that the results are a bit different from the muffin team, but we have the important feature that actually the system is an insulator in the bulk, and also but has states in the corner, in the Fermi level. So now we can actually see whether this actually describes the experiments that they have. So here I'm showing to you just a picture of the experiment. So here is one flake. And corresponding to this flake, we are showing here the density of states. So now here for experiments and also for the theory, pink is a very high density of states, and blue is not no density of states. So this is below the Fermi level, far below. So it's very low values of energy. Here you see that you have a state that's basically in the bulk. In this second row here, I'm showing the results for the muffin team. So this is how the potential looks like. So you see here that indeed you have this kind of region. I mean, basically we are modeling the potentials here where the electrons will not sit. And then again, you see that you have occupation of states in the bulk. Actually, here is not so high, but it gets a bit higher. And this is for the tight binding calculation. Now here we actually, for both the tight binding and muffin, we are keeping a same value of maximum in the density of states. So some features cannot be so clearly seen, but you're going to see that they are looking very close to the experiments. So here, I mean, it's not so visible, but have occupation bulk. The same here, but actually what's more and I mean, so these states for low energy, they are just bulk states and not so interesting. While close to the Fermi level, now we start to see these states that are localized in the corner. So here it's quite close to the corner. I mean, there's a corner state at 15 MeV. Here is 0 MeV in the tight binding model. Then there is a state here that's localized in the outer edges. Here appears a bit also in the inner. And then for a bit higher, you see that you have states that are mostly in the inner edges of the triangle. So this is a very simple model, not using ab initio methods or anything like this. But for us, and also if you look at the energies, they don't really match the experimental energies. But for us, it's quite nice because you could use a very simple model with just spin-off coupling, basically, and show that these states, they both appear just when you have spin-off coupling. And also that they follow this kind of energy distribution that kind of points quite a lot that these states are topological. So this for us, I think, was a very, very nice result. So it's something that we are very, very happy with. And also you could understand some features of the experiments, because if you look here in this state, actually, you don't see three corner states as you see here and here. And this we could understand as being related to the fact that you have some kind of asymmetry between the structure that you have in the system and also how the edges look like. Also, the edges are sharp, while if you look here, our simulation, the edges are a bit wiggly. So for some topological states, actually, this depends on dissemination. So we are able to actually reproduce this kind of features just by rotating the instruction, also using sharp edges. So this was something nice. And I mean, aside from the fact that these states have very high spin-off coupling, I mean, need to have very high spin-off coupling. And also, if you look at literature in bismuth, it's predicted to have the topological state. So basically, when you have a fractal, you're creating more holes on it. So expect this state to be topological. Also, there is something that at least theoretically you could investigate. That was actually look at the effect of disorder in these states and see how robust they are. So this we did using this bismuth thinking calculation because we could have more freedom of looking at disorder. And then we do disorder like we add a lot of different shapes on the system because if you remember the original experimental picture was quite nanoscopic, so you see a lot of different states. So we could be able to do that. We see that these states still survive. You have the topological states here that survive and that they are very, when you really look at a lot of flakes, they are a bit more chaotic. We did also, here's a bit, it's not very clear to see, but I can show the pictures if you wish with more disorder. And here I'm doing disorder in the values of the height of the potential that we look at your confined electrons. And we can see that the states don't change. Also the same with here, also things a bit difficult to see, but we're doing some disorder in the position of the scatter. So basically is a kind of making the system become more amorphous. And we don't see the state changing here. So for this value of disorder, things a bit difficult to see, but I can show you some values with more disorder. And you see that the bulk is completely delocalized. So not localized, actually you destroy the bulk state. So you see more localized states, but they're not really uniform. While the states really remain in the edges of the system. So it's a very strong symmetry that these states are topological. So this is more or less what I wanted to talk to you today. And I want to just give you some conclusions on that. I hope that the talk was clear and that you could understand a bit why topological states are interesting, that they find this kind of new phases. And also they are useful for these quantizations. And what I really wanted to convince you today is that if you just take bismuth and put on indium timonite, you form the self-assembled fractal lattices with common edge states. And these are quite well described by this theory, just doing a lattice with strong spin-off coupling. So I think this was a nice result that we have. And of course, there are still things that can be interesting to do. So I think also we want to look at other kind of topological phase. For instance, looking at topological superconductivity can be quite nice in it. But there are still some things. I mean, in this case here, we're not really compute the topological invariance for the system, but I think it's something interesting to look at this complicated model and try to see whether can show that we have quantized topological invariance. And also, this is especially something that I like to do is to do other experiments that directly address topology. So for instance, look at the whole conductance that I showed you at the beginning that actually was the way that you start to realize that topology was important at all, right? So with that, I conclude. I thank you very much for your attention. Look forward for your questions. Thanks a lot.
Thank you very much, Rodrigo Arouca. Muchas gracias, Rodrigo. Muy boa palestra.
Muito obrigado.
Perfecto, excelente. Agora vamos a pasar con las preguntas dos panelistas. Now we are going to start with the question from the panelists. First, la pregunta del profesor Stuart Holmes del University College London, University of Cambridge. Stuart, you there? Your camera, please.
Thank you, Professor Arouca. Very interesting talk. Can I check on the experiment? I know your talk is mainly a theory talk.
Mm-hmm.
What experimental data is being taken? Is it a tunneling spectroscopy? Is that the data?
Yes.
Maybe...
So,
you're sensitive to density of states with the tunneling process.
Yeah, exactly. Yeah, exactly. Yeah, sorry, I should maybe have been a bit more clear on that. So actually here, I mean, they have they do all the measurements with this scanning microscope. So here they're doing spectroscopy, So this is basically the main thing that we try to describe in the theory. I mean, the experiment also is mainly that. But also here they can use it, of course, you have the topographic images as well. So then it's a way to know exactly, I mean, if you're in the flake or if you are like in a more to the number of bismuth layers that you have also in the sample here, because also important to know, I mean, this for the modeling.
Can this is perhaps a little unfair to ask this question. Can this experimental technique differentiate between a surface state and a bulk state in the bismuth?
Sorry, can you repeat your question? I cannot hear as well.
In the data, can the data differentiate between a bulk state in the bismuth and a surface state?
Yeah, so here I think, let me check if I have extra slides with that. No, unfortunately I don't have, but if you look in our paper, there are two ways that we differentiate that. First of all is looking at the spectroscopy. So if you look at the spectroscopy, you can see, for instance, that the substrate is completely gapped. So actually none of the physics that you're seeing is associated with the substrate. I mean, substrates will influence a bit on Rashi-based spin-out coupling and these kind of things, but not necessarily that we are measuring. And also, if you look at the topographic image, also you can kind of clearly see that you have some dips on the SM when you look at the voltage. So actually, it's telling you at least the height of the flakes that you're measuring. So I think with that, we are a bit confident that they actually can tell apart all these different regions here.
I mean, it's very interesting that it self-organizes into this gasket structure.
Yes.
I've never seen that before in this material, so it's very interesting.
Yeah,
sorry, continue. Sorry, I interrupted.
No, it just should mention that, I mean, this is also something that I should have mentioned, that there will be at least two independent groups that look at that in sorted state. So also for us, I think it's for experiments also important to know that it's reproducible in some sense. So I mean, but the indium timonide substrate is quite important, I think, to see this.
Yes, I think also the doping of the bulk will depend on critically on the substrate, whether it's indium or antimony terminated. I know that's not the subject of your talk, but there'll be some detailed chemistry which will set where the chemical potential is in the bulk band structure. That may be fundamental to whether you see the surface states.
I think that's very interesting. Yeah.
I have one final comment. That's on the fractal dimension of the gasket. It's my understanding, if you double the length of the side of the triangle, you don't increase the area by 4, you increase the area by 3.
Exactly.
Dimension should be log 3 divided by log 2. Would that be correct?
Exactly. Yeah, that's precisely that, because if you look at the exactly, because here the area, I mean, when you're doubling the base, you're actually having 3 more triangles.
3,
so
not
then
4, it's 3.
Yeah, exactly. Yeah, exactly.
Thank you. That's a very interesting talk. Thank you.
Thank you a lot. I really appreciate it.
Thank you very much, Professor Stuart Holme, for your questions. Bien, ahora pasamos a las preguntas del profesor Mauro Doria, de la Universidad Federal do Rio de Janeiro. Mauro.
Hello, Rodrigo. Very nice talk. Congratulations.
Thanks,
I would like to understand a little bit more where is the importance of bismuth and its properties into this fractal system, or if it can be replaced by some other element.
Yeah.
Could you tell me what's important of bismuth? Because I consider bismuth very interesting material. But first I want to ask you why do you, I mean, where it enters. I see you talking a lot about the fractality, but I don't understand why bismuth is important.
Yeah, so first of all, I'd like to thank you for being present also. I mean, you was lecturing many parts at attending Rio, so I really appreciate you being here. So now about the physics and the bismuth. The first thing is that, I mean, at least for the best of my knowledge, this is the first, I mean, bismuth from indium timonide is the first example that we really saw these fractal flakes. So, I mean, by itself, I think it's quite important here because, I mean, I don't know so much about ab initio methods to understand exactly, okay, if you change bismuth by a different material or indium monazite by one, how you can actually obtain the same physics for the structure itself. But for us, I think the main important point of being bismuth is that it has a very high spin-off coupling. So it's the same reason why when you look at these experiments here, actually you just need bismuth to see this, because it's a material very high spin-off coupling in a honeycomb lattice. Also forms this honeycomb-like lattice as well, at least for these substrates. So basically for us, it's the important point. And if you look at the modeling that we did, I mean, the only important point, for instance, this one, I mean, there's no information on bismuth at all, aside from the fact that it has a very high spin-off coupling, right? So basically has this parameter here will be quite high for bismuth. So if you can have a material that also has high spin-off coupling, for us is the important point. So, I mean, at least theoretically, if you can have a fractal lattice that with a material that has high spin-off couplings already enough to see the same states.
Okay, thank you.
Ok, muito obrigado, profesor Mauro Doria, de la Universidad Federal de Río de Janeiro, por sus preguntas. Ok, bien, agora ao público, se el público tiene preguntas, el público latinoamericano, deje sus preguntas a través de las redes sociales donde están siguiendo esta transmisión urgentemente. Al final leemos si es que hay alguna pregunta del público. Perfecto, ahora pasamos con las preguntas del profesor Sergio Conejeros de la Universidad Católica del Norte en Antofagasta, Chile. Sergio.
Yes, I'm here. So can you hear me?
Yeah, can you go?
Okay. Many thanks, Rodrigo, for your interesting talk. I have here in this equation, why is it so important to consider the spin orbit coupling?
Yeah, so thank a lot for.
Is it important? Sorry, is it important for all the calculation or just for instance for when you are working with atoms that have lot of electrons?
Yeah, thank you a lot for the presence and also for the question. So the important point here is that, I mean, for us, the spin-off coupling will act, as I mentioned, as this kind of artificial magnetic field for different spins. And then it will make the circulation of the states and both the presence of the states localizing the edges that are related to the topological features of the system. So in the first row here, I'm showing the states without the spin-off coupling. And then I mean, they are interesting by themselves to see that you can see the properties of this fractal structure, but you don't see any states localized in the edges in the corners of the system. So actually you need to have them to see these states. So that's what we want to model in the experiments. So it's important to have, I mean, but this method of using this muffin team method actually is a method that people use for ab initio calculation. So in principle, don't need to have spin-off coupling. You can also model all the materials with that. So I think it's quite successful method to model real materials.
Okay. I have another more general question. I have some problem with the internet connection. Probably I don't know if you're already told something about it, but I would like to know how expensive, computationally speaking, how expensive are these calculations? So do you need I suppose you need a supercomputer for or a computational?
No, actually no. No, actually this is a good point. I should maybe have mentioned that. But this lattice that we have is not really that big because, so if you look at here, as I mentioned, we are doing this kind of discretization of grid. If you wanted to really have like higher generation, then you need to have it to get better results. So really, for instance, if you go closer and closer to the limit, maybe let me go here, closer and closer to the limit where you have this lattice here that's really infinite, you need to have it a better computer. But the simulations that we did for this paper actually will run in our personal computers, so it's not that heavy. The only trick is that, I mean, if you look in terms of grid is a 200 by 2. No, the largest one that we use is 300 by 300. But then we do not take all the energy levels. We just took the energy levels close to the Fermi surface because these are more relevant ones for us. But it was really not expensive calculation.
Okay, Thank you very much again for your good talk. Thank you.
Thanks.
Muchas gracias, profesor Sergio Conejeros de la Universidad Católica del Norte, Antofagasta, en Chile. Bien, Rodrigo, você sabe que la próxima semana tenemos otro invitado también especial, que es el profesor Alexander Hernández de la Universidad o del Centro Atómico de Bariloche. Él ahora está conectado y seguramente tiene algunas preguntas. Hernández.
Thank you, Luis. Very nice talk, Rodrigo. I have a few questions. For example, in your case, it's related with the question of Rodoria. When you choose the parameters of the type banding calculation, for example, these parameters are related with the material, specific material. How at the end the parameters were chosen in this case?
Yeah, so thanks a lot for your presence and also the question. So here for us, we just I mean the specific form of the type binding, we just did like took spin-off coupling, did this like the cluster calculation for it. So actually we use the things that we expect to be important for bismuth. So and then I mean if you look at other calculation in bismuth, you know that this X, PX, and PY optals will be the more relevant. So I also look all the hybridizations that they have. But since there's no ablation calculations for this material in specific, we took the ones from bismuth and actually just changed a bit because our idea is not really to do like ab initio modeling of that. And I think, as I mentioned, in terms of the energy levels, they're not really correct. But we just wanted to do like a kind of minimal model for the system to actually understand that. So I mean, the specific terms that we have, we use from the cluster, but the values itself, we just choose the ones that were closer to the experimental results. So it was a kind of fitting. It was not really ab initio.
Okay, thank you. The last question is related with this model. Now you have more information. That information that you have with experiments. For example, did you study the binding structure of this? If you can define the binding structure in this case, and the topological state is supposed to be at the surface. If you, for example, can be sure that in the bulk, if you in this case you can define a bulk because it's a different structure, it's like a fractal. If the material has a band gap in this case, for example.
Yes. So the part from the binding energies, you mean binding energies really of the like to create a lattice, right? Or
the question is if you, in this case, can have more information that you have from the experiments, especially the band structure of the material, for example.
Yes. So I mean, this part on the determinate states are really in the band structure. Okay. So the band structure itself, we have some. I mean, with spectroscopy, you can have some information on that. This we do not try to match precisely. We look more on the density of states, the density of states in space. But in terms of, I mean, looking at this spectroscopy there, we can actually see that the states is gapped in the bulk. So I do not show this, but in the paper we actually have experimental, at least. Because I think the band structure, I mean, the band structure, we do not show the theoretical one. But also we saw that, I mean, you have some states for the bulk, then you have a gap, it states from the edge, gap, states in the corner. And it is also in the experiments they see as well. You see that really the bulk is insulating. They actually have a quite nice, they have a quite nice image, unfortunately not to the slide, but when look here, for instance, they take one of these flakes, and with the SM tip, they follow the edge, and then following the edge also going a bit in the bulk, and then you can see that the states are just localized in the edge. It's quite nice picture. Unfortunately, I do not touch the slides. But here you can see in the archive at least. Sorry. In the archive here you can see the image.
Thank you very much.
Thank you.
Ok, muchas gracias, Alexander Hernández. Bien, ahora tenemos también otro invitado, el profesor Marco García de la Universidad de Coahuila en México. Marco, ¿tiene una pregunta? Marco García.
Good morning. I have no questions.
Ok, no hay problema, Marco García. Bien, Margarita Sánchez, también de México, Centro de Estudios Avanzados en Nanomateriales.
Hola, hi, good morning. It's Advanced Material Research Center, is CIMAP. I'm a chemist, so I'm curious about the synthesis, but maybe you don't have information about that. Everything was very interesting. Thank you very much.
Yeah, thank you very much yeah, unfortunately I don't have I mean, yeah, I don't know because I really like this was the part of the experimentalist. I mean in the manuscript described. Something also, I mean, maybe that I can mention, I do not, unfortunately, don't mention it 4 times, but actually, but actually, you can see some quite interesting, there are some quite interesting studies of these fractals in chemistry. So, I mean, this realization in chemistry of fractals of 2015, also there are a lot of interesting results on that, unfortunately, I mean, both because of my lack of knowledge on chemistry, but also because of time I was not able to cover.
But for you, maybe in the physical review letter, yes, maybe it's detailing there.
Yeah, there is quite detailed. Also in our paper is also detailed, but also sorry. Here is quite detailed. Also, for instance, there is some DFT study at least to show how the structure is formed. So actually, they do some analysis on why for this specific kind of substrate you form the states or not. So there are some parts that I think is not very correct. For instance, here they predict that you should not have topological states, but I think it's because I think they use the wrong model of the material. But I think for this part of the structure, it's quite well explained.
Thank you very much.
Thank you.
Gracias, Margarita Sánchez. Bien, si es que hay preguntas del público, Ximena Velázquez, James Godoy, si es que hay preguntas del público.
Buenos días, profesor Luis. No, en este momento no tenemos preguntas del público de la Universidad Nacional de Colombia y pues yo no tengo muchas preguntas al respecto. Gracias al profesor por la interesante charla que nos acaba de dar.
Ok, bien, perfecto. Entonces no hay preguntas del público. Y para mencionar que en estos momentos me encuentro en Caruaru, en Pernambuco, visitando al profesor Augusto Moreira, que es un gran profesor pernambucano, nordestino, y tiene mucho financiamiento, es un poderoso profesor, y vamos a buscar proyectos en conjunto, y está dispuesto también a colaborar con toda la red latinoamericana de física, materia condensada y ciencias materiales. Perfecto, pronto daremos más detalles y vamos a también invitar al profesor que dé una palestra en las próximas semanas. Bien, muchas gracias, Rodrigo. ¿Alguna palabras para decir despedida al público?
Yeah, so yeah, thank you again a lot. It was really, for me, it was really nice opportunity both to give the talk and also I think to know all of you. So I really enjoyed. I really congratulate you also for the initiative. And yeah, I think it's more or less that. So yeah, thank you a lot for all your attention, all the interesting questions and discussion.
Sí, vos sabe que esto es nuestro tercer año. Vamos 3 años de transmisión ininterrumpida todos los sábados. En la próxima semana, el otro sábado, tenemos al gran profesor Alexander Hernández del Centro Atómico de Bariloche en Argentina, que va a dar su palestra también. Vos está invitado también para que atienda. el próximo sábado. Sin embargo,
yeah, for
el
sure.
próximo sábado, sí.
No, I'll
Sin
for
embargo,
sure, I'll try to be present, yeah. Because the next Saturday is Midsummer, so it's a bit of a special day here in Sweden. But I'll try to to go out a bit of the festivities to enjoy a bit of physics as well.
Okay, understand. But próximo sábado, Alexander Hernández va a dar su palestra, pero sin embargo, yo a esa hora yo voy a estar en pleno vuelo hacia Lima, estoy yendo a Perú. Seguramente va a moderar otro de los miembros de la red su palestra. Bien, muchas gracias entonces, Rodrigo Arouca. Puede usted dejar de compartir su panel y vamos. Everybody is invited to open their camera, please, and to open your microphone to say goodbye to your microphone as well, to say goodbye to hasta luego, ¿no? Al palestrante del día de hoy. Abran sus cámaras y sus micrófonos.
Hasta la vista.
Hasta la vista.
Chao, chao.
Chao, bye bye.
Hasta la
Un
vista.
saludo a
Hasta
todos.
la vista. Chao. Muchas gracias.
Yeah.